All right, hello. Welcome to Explaining Explain, a deep dive into explain plans. My name is Richard, and I will be sharing my presentation with you. Just first off, just want to thank you for attending Postgres Vision, and also for just attending my talk as well. I know most of you guys have other responsibilities, so I really appreciate you guys taking the time to step aside from work and listen to our talks for this couple days. Just quickly to introduce myself, I am a support engineer for Enterprise DB. I also previously worked as a DBA and a web developer, and I've been using Postgres since version 7.4, so it's been a while. As a support engineer, we support several of our customers, ranging from small startups to large government and financial institutions. And we get a lot of emails asking for help on things like corruption or database performance and replication, all that kind of stuff. And one of the most common questions that I encounter is, why is my query slow? This is definitely a very important question, especially if you are working with many customers. You are trying to keep good performance on your database so that your applications are working well. So my answer to them is, let me explain. Not just explaining the reason why it's slow, but also just teaching them how to use explain, because explain is one of the most useful tools for anyone trying to improve their database performance. It's included in Postgres, nothing to install, and it's pretty easy to use. So in this talk, we're going to go through this feature in increasing detail. Just a quick roadmap of what we're going to do. We're going to talk about what does explain do. We're going to also tell you how does explain work, and then we're going to go ahead and look at some explain plans and try to interpret them. And we're going to talk about the scans and the joins and all that kind of stuff, just to get an idea of what explain is trying to explain to us. And then finally, we're going to show some non-trivial real-world examples of how explain can help you in trying to improve your performance on your queries. Okay, so let's dive right in. Okay, so what does explain do? Okay, explain is something that you append to your query. So if you have a query like select star from accounts, you say explain select star from accounts, and then it will explain to you what Postgres plans to do for that query. So it gives you some visibility into what Postgres is doing under the hood at the query planner and query executor level. Okay, now if you do explain analyze, what that will do is it will tell you what Postgres did for the query. So explain just tells you what it plans to do. Explain analyze tells you what it did. Okay, we'll go into that a little bit more in the next few slides. So moving on. Now, what doesn't explain do? Well, explain won't tell you why the query planner made some choice. It won't tell you, oh, here's why. It won't tell you why it chose a sequential scan instead of an index scan. It won't tell you about query performance being affected by another session, meaning that in your database you can have hundreds of connections coming in, and everyone's trying to select from the same table. Explain won't tell you that, hey, your query was slow because these other connections were locking the table or preventing you from scanning it faster. Explain also won't tell you about stuff that's happening outside of the database. So like, let's say in the OS level, maybe someone's doing a backup of your file system. Maybe there's some kind of auto scan of a virus software. Those kind of things are not going to be reflected in explain. It also won't tell you stuff about environmental factors, like let's say you have a congested network. It won't tell you that kind of stuff. Explain only tells you what Postgres intends to do or did through the query planner. Okay, so I've been talking a lot about the query planner, so you're probably wondering, okay, so then how does the query planner work? As you read explain output, you get to see how the query planner made what the query planner chose. And the way that the query planner works is that it will take a cost-based approach towards all the steps that it needs to do to run the query. So you're going to select some columns, you're going to pull up data from some tables, maybe join the tables together. Maybe you need to sort it, and then you got to limit. Those kind of different keywords in your query are going to be broken down by the query planner. And then for each actionable task, like scan the table or scan the index or join these tables together, those are all going to be associated with a cost. Okay, now those costs will be calculated based on two factors. It will be calculated based on table and index statistics. These statistics are stored in the database under a table called PG statistic. Now, this is all internal data. It's not something that's human readable, so you wouldn't want to look in there. However, Postgres does give you a view into that table, which provides some histograms, some statistics on some values in the database or in the indexes. Okay, and that's in PG stats. And even that's a little bit hard to interpret for some people. So if you're adventurous, you can look in there. Now, this information is refreshed through analyze. Now, don't confuse this with the explain analyze that I mentioned to you earlier. This is a separate maintenance keyword. So you say analyze table name instead of explain analyze query. A lot of times you might see this coupled with a vacuum. So you might see a vacuum analyze. So they'll vacuum the table and analyze it at the same time, just so that all the statistics are most up to date for the query planner to make its choices. The query planner also makes its choices based on the configuration that you have in PostgreSQL.com. It uses things like enable underscore star. So like enable underscore SQL scan, enable underscore index scan, those kind of parameters, when they're turned on and off, the query planner knows, oh, I can use these methods of joining the tables or scanning the tables and stuff like that. The configuration also has these cost parameters. These cost parameters are the values that the query planner uses to calculate cost or how much it takes to actually run this operation. So like a sequential scan, what will it take to scan the entire table? All that stuff you can actually turn on and off and tweak in PostgreSQL.com. And here's a listing of all those parameters. Now, it's actually kind of intimidating, but something I want to make you aware of is that you don't have to tune these much. Unless you're actually trying to coerce the query planner into making a certain kind of choice. And you wouldn't do that in PostgreSQL.conf because you would these would be globally changed, so you would affect other users as well. So what you would do is you can actually set these values on and off and change the cost in your live session. So if you're in PSQL or if you've got a database handle through some GDBC connector or something like that, you can actually change the cost within that session. And that way you don't affect other users. If you want to see what your current values are, you can actually run a query, this one right here. So you pull out as PG settings, look for enable and look for costs, and you get to see the values that they're already set to. The only ones that you really need to change at a global level are random page costs and sequential page costs. These are values that are relevant, especially if you have newer hardware. So like if you have like SSDs versus spindle disk, you can actually turn random page cost down because it's less costly to do an index scan or a random page fetch out of the disk. Moving on, so let's talk about what explain does. Like, how does it work? Okay, so we're going to give you like a real example here. So I loaded up pgbench and I opened up PSQL. And then so I run explain select, so no analyze, and I join the accounts tables and the branches table. And you can see this output. It says, okay, well, here's the query plan that the query planner came up with. It says, I'm going to do sequential scan on both of those tables that you want me to join, and then I'm going to join them together with a nested loop. And you can see the cost that it estimates. So it says I have 999,000 rows to scan for the accounts table, and then so that cost is $28.90 to do the actual scan of that whole table. Now you might be wondering what that left-hand number is, the 0.00. That number is the amount of cost to set up the operation. So in this scenario, The cost to start a sequential scan is 0 because you don't need to prepare anything. You don't need to pull anything into memory. You can just open up your file handle and start scanning out of that disk. So now you might be wondering, so where does this 2890 come from? So here's that query plan again. Okay, and here's actually the cost breakdown. Okay, so the cost breakdown is calculated in number of blocks on disk times the sequential page cost. So that's the sequential page cost, the cost that it takes to scan that table and all the blocks in it. Okay, plus the number of records times the cost for the CPU to read that tuple. And then you add to that the number of records times the CPU filter cost, which is the cost for the CPU to make that choice whether to keep that row or to discard that row based on the where clause in your query. Okay, so now we break that down. We say, okay, let's get the relation size. So let's see, the PG bench accounts is 13 megabytes. Okay, 13 megabytes, divide that by the block size on disk. So that you take 13 megabytes divided by 8 kilobytes, you get 1,640 blocks. Okay, so you're going to do 1,640 blocks times the sequential page cost, which is going to be 1640. You add to that the 100,000 rows that were initiated in PGBench times the 0.01 CPU tuple cost, plus the same 100,000 rows times 0.0025, which is the filter cost. You add that all up together, and there you get 2890. Okay, and that matches up with what we saw in the query plan. So as you can see, this cost-based approach is what the query planner takes to determine what it's going to take to perform this query. Now, what you didn't see is that the query planner also considered other options. So let's say it's considering maybe we want to do an index scan, maybe we want to do a merge join instead of a nested loop. All those costs were calculated, and the cheapest one that it could come up with is this one that we see right here. Okay, so let's actually run this query instead of just getting the plan. So let's find out what the query planner did, query executor did when you do this query. So you do explain analyze. Okay, so now here we see explain analyze in the same query, and we actually see the same plan, except not only do we see the cost that it had estimated, we see the actual values. So the actual time it took to perform that sequential scan and that nested loop. And then it shows you the actual number of rows that it encountered during that operation. So this is actually very useful for developers and DBAs who are trying to identify where the bottleneck is. So if you look at here, the most time-consuming part of this operation was the nested loop. The nested loop was 56 milliseconds, which isn't that much in this situation. But if you had a really poor performing query, you could actually look at these actual times and try to find out where that bottleneck is and start your search and your analysis from there. Okay, so now if we do explain buffers analyze, you not only get the information that we were looking at earlier, we get even more. We get to see the buffers that were hit in the cache and buffers that had to be read in from the disk into memory. So we ran explain buffers and analyze, and then we actually get to see these shared hit and read values. If we look at the very bottom, that sequential scan shared hit equals 2, so it found 2 blocks in memory, and then it found 1638 blocks it had to read out of disk and into memory. Okay, so if I actually ran this again, I'm going to get a higher value for hits and a lower value for reads. And if you see a lot of unexpected reading out of the disk, you might need to increase shared buffers because the stuff isn't getting stored into memory, into the cache, and you keep having to pull stuff out. And that's an indicator of maybe you're not using enough memory and you need to increase that value. Okay. There's other stuff besides buffers and analyze. There's other things like timings. It'll give you more detailed timings in the output. You can actually format this in JSON to send to monitoring software like Datadog, stuff like that. I want to get more into the details about how this query planner makes its choices between different methods for the execution of the query. So the fundamental building blocks of the query planner's operations involve joins and scans. Okay, so let's just go quickly through how these joins and scans work. Okay, now if you can see here, I added some more rows into the branches table. So now I have 100,000 rows in accounts and 100,000 rows in the branches table. Okay, so now I want to do a select and join them, same operation, same query. Now, because there's more rows, we're not going to see the nested loop again, because that nested loop is most suitable for small tables, right? And now we have equally sized, largish kind of tables. And actually what we're going to see now is that it's going to do a hash join, okay? Now, it decided that, oh, I think a nested loop is going to cost too much, right? It took all those sequential page costs and CPU tuple costs and all that kind of stuff and did the calculation and said, nope, nested loop is too expensive. We're going to do a hash join instead. Now, let's say I actually want to limit my search even more. So here we are with more rows, and I have AID is less than 100,000. Let's bump this down, and we're going to do AID is less than 100. Okay, so I want less rows, even though there's a lot of rows in the database, in the tables. This time we run it, we're going to get a merge join instead of a hash join. So nested loop, right? It's going to take, you have a table A, you have table B, and you want to join these two together. You want to get data from both tables that match a certain set of criteria. So what you're going to do is you're going to look through A, and then for every row in A, you're going to look through B for those values, right? And then you keep going. It's kind of like a clock, right? So as you can see, if I'm going to do this B scan many times, that the larger B gets and the larger A gets, the more time consuming it's going to take. So this nested loop is actually best for small tables. Okay. Now for larger tables, what you want to do is you want to do a merge join. So you take two larger tables, you merge them together like a zipper, right? Now this could be fast, it could be slow. It'll be higher. It'll be slower if the data is not already sorted. Because when you want to merge together, you take the corresponding rows and you match them together like a, like the interlocking parts of a zipper. But if you have to actually sort it, you got to do the sorting first and then you join it together. That's going to take more time. The other option that I showed you, if you might end up seeing the query planner do a hash join. Okay. Now the hash join, what it does is it takes the data from table B and it hashes into all the rows into values, and then for A you hash the value for each row, and you look for a corresponding row in B, right? So as you can see, you have to hash all the values in B, so that's going to be a high startup cost. Okay, but once you have done that, you're going to take A and you're going to compare them all, and that comparison is really fast. Just kind of quickly go through some of the ways that our scans can be improved. So this example, once again, we have a scan on PG Bench accounts with BID equals 1. Okay, so it's going to do a sequential scan because it doesn't have an index, right? And it takes 41 milliseconds to do that table scan. Once I create the index and I have a pretty low random page cost, the query planner is going to favor this index scan. So then when I run explain analyze, I say, hey, I got the query planner chose to do an index scan. Great. And my execution time dropped from 45 milliseconds to less than 1 millisecond. So you can see, if you can get your query planner to choose an index scan, you might actually end up with a faster query execution. An index scan is, as you saw, it was pretty fast. scanned to where BID equals 1 and then got the address, pulled it out of disk. Now, in this situation, we can actually, depending on your situation, you can actually get even faster. Now, let's say I got select star from pgbench accounts where AID is less than 1,000. Now, I'm doing an index scan because I know I only have to pick up 999 rows out of the table. And so it does, it scans for those rows and fetches them out from disk, and it takes 0.85 milliseconds, right? But now if you look at these the squares right here, the second query that I'm printing, it doesn't select star, it just selects AID. And because it selects AID and my index is created on AID, there's no need to look at the disk anymore. I can just look at the index, right? Because select star says, okay, so AID is less than 1,000. All right, these are the rows that correspond on the disk, so I pull them out. I need to pull out all the other columns because I want star, right? But if I do select AID, I'm going to look at my index, and I find all the rows where AID is less than 1,000. I don't need to look at the disk because I don't want any other columns. I only want that column that was indexed already. So then I don't have to do anything on the disk. I just get those values that I found in the index and I return to the user. And that takes a quarter of the time in this particular example. So I'm sharing this with you because as a DBA or as a developer, you want to craft your queries very intentionally, and you don't really want to be lazy about just, oh, I want everything and select star and and work with that all in my software, right? If you can get the queries tuned and you can get the database to do the work for you and give you just what you need, you don't have to do any extra. The database doesn't have to do any extra work, and you as a developer on your application side don't have to do any other work to sort and sift through all that data. Okay. So I just wanted to give you guys a quick example of how random page costs could work. These values are not really realistic. You usually keep random page costs to some value less than 10 or even 5. So in this situation, we see as I increase random page costs, I'm just demonstrating to you that the query planner decides at a certain point that, hey, it's too expensive to do the index scan, so therefore I'm going to do a sequential scan. And this would be true in a larger query example, which I wouldn't be able to fit onto this onto the slide. But if you're joining many tables together and you are trying to get a lot of data back after you join them, you might end up with sequential scans because the index scan is just going to be too costly. Okay. So just a quick overview again: sequential scan, index only scan. And then the bitmap pscan we didn't see here, but we might see in another example later on in this talk. What that does, it'll scan the index, building a bitmap of all the pages to visit. So it kind of pre-filters some of the stuff out of the table. And then once you've built that bitmap, you actually go fetch them out of the table. So you don't actually have to scan the entire table. So you scan the database, scan the index, and then you pull stuff out of the table selectively. Okay. Okay, so we're going to switch gears here. We're going to talk a little bit more about what Explain can show you and what it can do. Okay. So so far I've been talking about the scans and the joins and how the query planner makes those choices based on the cost. Now, what if the query planner has insufficient information? So this example would show you that, right? So we have two queries. They're exactly the same. Now I know that AID is not that big, and why is it not using the index kit that I created? What you would want to look for is stuff like this. These where the rows don't match between the estimated and the actual. Okay, so as you can see here, the estimation is 30 times higher than the actual number of rows. So you can see, hey, the query planner was thinking, hey, I think it might be too expensive to do an index scan because it's going to cost me so much. So I might as well just do a sequential scan on the whole table. Okay. And once you analyze it, it discovers, oh, actually, we only have, it's not completely accurate either after you do the analyze, but it's definitely not orders of magnitude off. And it decides, oh, actually, it's not that costly, so I'm going to do an index scan instead. The tip here, you want to analyze after you create an index, and you want to vacuum and analyze your database as often as you can. Okay, because that way you can keep the most up-to-date statistics for the query planner to use, and auto-vacuum can help you with that. Okay, the way to tune auto-vacuum, you would want, I think that's kind of outside of the scope of this talk, but just bear in mind that's something for you to Google about and to make sure that your settings for auto-vacuum are set well and aggressive. Another thing that Explain can tell you is if you have insufficient memory allocated. And in this example that I'm sharing with you, you can see that that second line after sort method. So it did a sequential scan on the history table, and then it needs to sort it because you're ordering by the delta column. Now that sort, it spilled to disk because it's an external operation on disk, and it took 2.6 megabytes. Okay. The fact that it had to go on disk means that it could not do it in memory. And where does Postgres do its sorting in memory? It's in workmem. So if we see workmem, there's actually 4 megabytes listed. So it's probably spilling out because it was an operation that take maybe like 7 or 8 megabytes. So I bump it up to 16 and then run it again, and there you can see that instead of external merge disk, we see quick sort in memory. And the memory, we actually took up 9 megabytes. Okay. So what this tells you is that while you shouldn't boost workmem globally, you might need to do it at a per session basis. So Explain Analyze saved the day here by showing us that it required a merged disk, and if we bump up workmem, we actually get a better performance. Another way to that Explain can help you is by showing you how it interpreted the where clause. So the where clause, the way that you write it will actually affect how whether Postgres the query planner will choose choose to use an index or not. So it's not just based on the cost, but also based on how you write the query. Okay, so in this example, I've created an index on pgbench history, and that index is based off 2 columns. It's based off the AID column and then a substring, the first letter of the filler column. Okay. Now we've had situations where the customers, they will write queries. So like here for example, I use the AID and then I use the leftmost character of the filler column. And when you do that, you actually end up with a bitmap heap scan. That's not a full index scan. It used the index and tried to grab all the IDs where it's 10,000, and then it rescanned it and filtered based on that function filler, a left filler. Okay. And let's say another developer wrote his query like AID equals 10,000 and substring lower filler. So he wants to, sanitize his data. He wants to lower all the values. And again, he gets a bitmap heap scan. He doesn't actually get a full index scan. And this is for the same reason. It doesn't know that filler is indexed it doesn't see filler indexed in that way. It's not indexed with a lowered substring. Okay. Now, finally, here's an example where you actually write your query and call the columns the exact same way that the index was written. And so I say substring filler 11 and AID equals 10,000, and then there you go. You see the index scan. Okay. So if you are wondering why Postgres, the query planner is not using a particular index, you might want to look at how you're writing the queries. Maybe it's not the query is not being written in the same way that the index was written, and you would have to make adjustments there. Okay. And another example, so these operations on a JSON column, this person was actually adding an extra JSON B array elements. Second one is correct call. Okay, so again, you have to call your query and call your index in the same way that it was written. Okay. Final example. So unexpected behavior. So you might see some unexpected behavior. I've had a customer where I've got this table. I've got 2 numeric columns and a bunch of text columns and a timestamp. And the update on that table, when I ran it with explain analyze, it was pretty fast. It was less than a millisecond. And the customer came to me and said, "Hey, how come it's taking 40 some milliseconds per update? That's kind of strange." Right, and we can replicate the issue by hand, because every time I did it by hand, I got perfect performance. So what we ended up doing, we installed the module, and the module printed explain analyze output to the log, and this is what we saw. Right, we saw 40.922 milliseconds, and what was actually happening was that the update was actually casting the numeric values into floats, double precisions, right? And that extra operation prevents the use of index scans, and then it just slows everything down. And the reason why this happened was because their ORM had a bug where it didn't know what to do with numeric values. So it just, by default, casts anything that it doesn't recognize into a double precision. And once we fixed that bug, we actually saw the previous performance less than 1 millisecond. Okay. So what was that module? That module was called auto-explain. And what that does is it prints explain to your log. It can do explain analyze. It can add the buffers, the cache behavior, format it as YAML or JSON, however you like it. You can actually trigger log the trigger statistics. If you do like an update, it won't tell you what the trigger did. But if you have auto explain on, it'll actually explain the update or delete, and then it'll actually create another entry on explaining the trigger behavior. So that might actually be very useful for some behaviors that you don't see. Now, the auto explain, if you do it globally, it creates additional I/O on disk, because it's all that extra logging activity and extra stuff that it has to pull out of its own out of memory. So rather than doing it globally, our recommendation sometimes is to just do it on a per session basis, so that you can actually just load, just auto explain just the stuff that happens for that one session. Okay. So that's all the time I have for my talk, and I hope that it was informative for you. If there's a few minutes left, I'd like to take some questions and answer any that you might have.
Hi, Richard. We have a few questions in the question and answer chat.
Great. Hi.
First
Hello.
one is that. Hello. First one that we have in the question and answer chat is how can we check whether the stats are updated or not?
Okay. I think the easiest way to check whether your stats are updated, remember that stats are updated through analyze. So if you did a vacuum analyze or an analyze on a table or database, that would be the way that the statistics would be refreshed. And the way to track that is that if you look in the PG underscore user underscore tables, PG stat user tables, that view actually has a column called last analyze and also another column called last auto analyze. And those are timestamps. So it'll tell you whether a table was analyzed or auto analyzed recently.
Okay. Another user asks, what would be a good random page cost value when hosted on Amazon RDS?
Okay. Yeah, I think when I don't have too much experience with Amazon RDS. I believe most of their hardware underneath is SSDs. So assuming that they are SSDs, I would just try to set the random page cost something very low, like 1. I believe you could even set it to a fraction. So if you want to experiment with lower values, like a fraction of 1, um, you could actually get some pretty good performance using indexes.
Okay, and another question, is there a concept like Oracle invisible indexes in Postgres? And if so, how can they be used and explained?
Okay. Oracle, I believe Oracle invisible indexes are just indexes that aren't used by the query optimizer or the query planner. And in Postgres, we don't have a syntax that would allow you to do that, but you could manually change the, I believe it's called the PG. Let me check. Yeah, if you look under PG index, there's a column called index is valid, but it's abbreviated as ind is valid. So INDIS valid. If you set that to false, it basically makes the index invalid, so the query planner doesn't use it for the query, but it still gets updated whenever you make any changes to the table. So in that way, it would behave like an Oracle invisible index.
So the next one, is there a way to give hints to queries to force the usage of an index?
I believe there aren't any query hints that you can give to Postgres, but if you're using Enterprise DB's Postgres Advanced Server, we've actually expanded the query parser to include hints. So yeah, if you want to use index hints, use query hints, you should probably be using Postgres Advanced Server.
Okay. Another user asks, is it worth forcing an index-only scan if there are a lot of columns returned?
Forcing an index scan when there are a lot of columns returned. So I'm guessing in this situation, you're going to do an index scan, which is a fetch of the fetch all the necessary rows you would want in the index, and then go to the disk and pull out all the rest of the data. I guess the query planner may settle for a bitmap heap scan in that situation, because that way you actually leverage the speed of filtering through an index, but you don't have to do all the like sequential scan through an entire table. So if you know you have a lot of columns that you're going to return, I wouldn't be too concerned if it settles for bitmap heap scan instead of an index scan.
Yeah, so a number of people use covering indexes to try to get index-only scans. I think he was asking if that's worth doing when there are a lot of columns you would have to add to the index.
Mm-hmm.
So do we have anything like plan table to store the explain plan? I think this person would like to select the data of the explain and store it somewhere.
Oh, I think we would, in my experience, that would be done through auto explain. So it's not the most ideal situation because you're not storing the explain plan into a database. but you're storing it into a log file, and you'll have to parse it later. If you are trying to force a particular explained plan, I think what you would do is you prepare a transaction or prepare a statement. So you use prepare a statement and then give it a name and then add the query you want, and you'd have to craft that so that you get the kind of explain plan that you want, execution plan that you want, and then you would repeatedly call execute on that prepared statement.
And then I think this is a feature question, like if it's on the roadmap, there's a question, will there be something similar to Oracle's Query Tuner?
I'm actually not very familiar with Oracle's Query Tuner, but I don't think I've heard many conversations regarding adding that to our enterprise EDB advanced server.
Okay, I'm just scanning to see if I've accidentally missed any questions, but I think that gets us to the end of the list. If anyone feels their question is being ignored, go ahead and post it again, and I will read it. Nobody's question is intentionally ignored. Here we go. We got some more. Are there any strategies for giant queries consisting of hundreds of functions and subqueries? Is rewriting language PL/PGSQL with SQL always improves performance, or not?
I'm sorry, I think I missed that one there.
I can answer this one from personal experience if you like.
Okay.
If you write something in PL/PGSQL versus SQL, you can end up having a different planning time if there's an execute statement inside your stored procedure, and you can sometimes get different performance, sometimes radically better performance if you had something really wrong with doing it as just a SQL function. But you know, this PL/PGSQL might be slower, so it's not a one-size-fits-all solution. All right, so the next question: how to justify scattered read Oracle does for full table scan to sequential scan in Postgres. I think they're looking at what they would be doing in Oracle with a full table scan and then moving that to a sequential scan in Postgres.
Yeah, I'm not too sure how to answer that question. Justify a scattered read, so Oracle does a scattered read when doing a full table scan. Yeah, I'm sorry, I don't really know the Oracle behavior and how to compare that with Postgres.
Okay, sorry to the viewer. I guess we don't have the answer for that. Another one is, do you have any suggestions for full text search queries? And I would have to think that this has something to do with planning. So is there an explain that you use to get better information about full text search?
Postgres does come with a full text search feature, and I think if you use the functions within that, I think it's an extension that you have to use. That would actually, that may not be related to the query planner itself, but it's something that, yeah, it would be external to the query planner, I believe.
Okay. Does a heap scan pull in multiple blocks? And then compare
a heap scan pull in multiple blocks. A heap scan will. So I guess the question is, if I scan a table, will it pull in multiple blocks? I guess the answer is yes, because you'd have to pull in multiple pages of data to process and filter. I think maybe the question is being, maybe the asker is asking if they would do the multiple polls at the same time. In Postgres 11 and up, we do have parallel sequential scan. So in that sense, if you have multiple parallel workers, you can pull multiple blocks simultaneously and improve your performance that way.
Okay. Next question asks if it's possible to create a column group for statistics collection to help with non-uniform data distribution.
So I believe this question is asking about correlated data. Is that right? Actually,
it sounds
yeah, I'll
right.
answer. Yeah, so like let's say you have like zip code data and state and city data, and all of those are correlated, but Postgres doesn't know how they're related. You can actually there's a feature where you can say create statistics and provide the related columns, and that will uh, tell the query planner that there are these correlations, and it will actually create a separate histogram based on those correlated columns. And the query planner will use that information if those queries appear if those columns appear in the query.
Okay. Another user asks, if an explain analyze is taking a long time to run, is there a way to see what's going on while it's running, or do you always have to wait for it to finish?
Yeah, there isn't a lot of visibility into why an explain analyze would take a long time to run. Now, bear in mind that explain analyze is identical to just running the query without explain analyze. So if it takes a long time to return, it's not because explain analyze is being slow. It's the query itself is being slow. And if you need to find out why the query itself is being slow, there aren't a lot of tools into analyzing currently running queries. You would need to access that information through the OS using like VMstat or even using like GDB to find out which table or what exactly the backend is doing. That requires a lot more in-depth knowledge of Postgres itself, and maybe even like knowing how to read through the C code. So if that's the case, you would probably be better off finding professional services to help you with that.
Okay. Another question relative to Oracle: can we keep objects in memory similar to the keep pool in Oracle? I think the user wants to ask if they can force something to stay in memory and not get evicted.
Yeah, I don't think you can pin stuff into memory per se. That is the purpose of shared buffers. So you would want to make sure shared buffers are sufficiently high and that the stuff that you have accessed remains in the cache.
Okay. Another question asks if there's a good book about Postgres query optimization that you could recommend.
I don't have any off the top of my head. I know that Marcus Renand does a lot of talks and presentations on query planning and indexing. So he actually has a website called usetheindexloop.com. So if you want to head over in that direction, there might be some good resources there to familiarize yourself with indexing and query planning and stuff like that.
Okay. We've got a question of a sort of generic nature. How best to tune workmem?
How best to tune workmem? I think in my experience, workmem, we generally tune it based on the available RAM. You need to bear in mind that workmem is is a per session value. So if you set it too high in PostgreSQL.com, it's going to have a multiplying effect. So you need to think about what your max connection is going to be, and you need to think about how much RAM you're going to have left over after shared buffers is allocated, and you'll have to divide that leftover amount by the max connections that you would anticipate. And you would want to tune that even further down because there's stuff that the OS needs to access in memory. So typically what I would do is, if I can afford to, I would set it to maybe like 100 megabytes or so, and then if I need to increase it, you can do it at a per session level.
Okay. And then a follow-up question. I think this is going to have to be the last question because we're running short on time. Just a follow-up question on covering indexes. What are the pros and cons?
Yeah, I don't have any pros and cons for covering indexes. I think the pro is obvious that you actually get to do more correlations and get better query planning, but the con would be that it would just create extra overhead for maintenance.
Okay, well, thank you so much. That's all we have time for today, and we may try to get answers to the rest of these after the talk.
Great. Thank you guys very much for attending this talk.